Okay, let's start with something familiar. You know when you flip a coin, like loads and loads of times,
Mm-hmm.
you always end up pretty darn close to 50-50, heads and tails. It's weirdly consistent.
It really is. It feels almost inevitable after a while.
So the question is that just a coin thing, or is it maybe pointing towards something? Well, something more fundamental happening underneath all that randomness.
That's a great question. And yeah, it's definitely a glimpse into something much, much deeper. What we're really seeing there is the law of large numbers in action. Let's call it LLN.
LLN.
Think of it as like a fundamental principle. It brings a kind of predictability out of chaos, a shortcut to seeing order where things look random.
Right. So that's what we're digging into today. We want to unpack this LLN, figure out how it works, what it means for, fair games, but also biased ones.
Exactly, and how it actually shows up in your world, probably more often than you think.
Okay, so to get our heads around this LLN, maybe we should start with the basics, like how we even talk about randomness.
Good idea. So anytime you do something with an uncertain outcome, like rolling a die, that's a random experiment.
Yeah.
Simple enough.
Right. And the results you can get, like rolling a 1 or a 2 or whatever, those are the outcomes.
Precisely. And the set of all possible outcomes, 1, 2, 3, 4, 5, 6, for a standard die, that's your sample space.
Got it. So then there's what should happen, mathematically speaking.
That's the theoretical probability. For a fair die, each side has a 1 in 6 chance. That's the theory, the ideal.
But then there's what actually happens when you start rolling it, which is often quite different, at least at first.
Exactly. That's the experimental probability. You roll it, say, 100 times, and maybe you get a 4 12 times. So your experimental probability for getting a 4 by that specific run is 12 out of 100, or 0.12.
Which isn't quite 16, or about 0.167.
Right. And in small numbers of trials, it can be way off. You might roll 10 times and get 3 6s or maybe no 2s at all. It's messy early on.
Okay, so the law of large numbers. That's the bridge between these two, between the messy reality and the clean theory.
That's a perfect way to put it. The LLN guarantees that as you do more and more trials, and crucially, they have to be independent trials, one doesn't affect the next.
Like each coin slip is fresh.
Exactly.
Yeah.
As you increase those trials, your experimental probability, that messy real-world result, gets closer and closer and closer to the theoretical probability.
So eventually that 12 out of 100 for rolling a 4-liter would edge towards 16 or 17 out of 100, then 166 out of 1,000, and so on.
Precisely. It converges. Think about a casino. They might lose on one hand of blackjack, sure, but over millions of hands. The LLN ensures their small mathematical edge translates into very predictable profits. It's not luck for them in the long run, it's math.
So back to my first question. It's not just coins then. This applies across the board.
Absolutely. Any random experiment, if you had, I don't know, a fair 3-sided die, you'd expect each side to come up about a third of the time eventually.
And our 6-sided die, each face heads towards 16. Makes sense. But you mentioned something else. It applies to averages too.
Yeah, and this is really interesting. It's not just about how often things happen, but the average result. For a fair die, the average value of your rolls will get closer and closer to 3.5.
Wait, 3.5? But you can't roll a 3.5. The faces are 1, 2, 3, 4, 5, 6.
I know, right? But mathematically, if you average all the possible outcomes, 1 plus 2 plus 3 plus 4 plus 6, you get 3.5. And the LNN says the average of your actual rolls over thousands, millions of rolls will inevitably approach that 3.5 value. It's the long-term center of gravity, so to speak.
Okay, that's subtle but important. Now, what about bias? Does the law of large numbers somehow fix things, make a biased coin land 50-50 eventually?
That's a really common misunderstanding. And the answer is definitively no. The LLN doesn't impose fairness. What it does is incredibly powerful. It reveals the true underlying probability, whatever it might be.
So it doesn't correct bias, it quantifies it.
Exactly. If you have a weighted coin that's designed to land heads 65% of the time, the LLN doesn't fight that. It ensures that over many, many flips, you'll see heads roughly 65% of the time.
And a loaded die. Maybe one where rolling a 1 only happens 10% of the time, but rolling a 3 happens 20%.
The LLN will make those exact percentages emerge over enough rolls. It's like holding up a mirror to the system's true nature, bias, and all.
Wow, okay, so it's not about fairness, it's about convergence to the actual probability. So how does this LLN stuff affect us, in the real world?
Oh, hugely. Think about insurance companies. How do they predict how many claims they'll get? They use the LLN on vast pools of customers. One person is unpredictable, but across millions, the claim rate becomes stable.
And casinos, like you said, they rely on that long-term predictability of their edge.
Absolutely. That's also why statistics works for things like opinion polls. You don't have to ask everyone in the country. A large enough random sample, thanks to the LN, can give you a pretty accurate picture.
Which brings us to maybe the biggest way people get this wrong.
Yeah, I think so. It's got to be the gambler's fallacy.
That feeling that after a run of bad luck, your luck must turn. Or if a roulette wheel hits black 10 times, red is somehow due.
Exactly that. People think past results influence future independent events. But the coin, the die, the roulette wheel, they have no memory. The LLN works by swamping out early weird results with huge amounts of new data, not by correcting the past. Each new flip or spin is independent.
There's that famous story, isn't there, Monte Carlo?
Oh yeah, 1913. The roulette ball landed on black 26 times in a row. 26.
Wow.
And people went crazy betting on red, thinking it had to come up. They lost millions because they were betting against probability, misunderstanding how independence and the LN actually work. A very expensive lesson.
So summing it all up then, this law of large numbers, it's kind of profound.
It really is. It's this core mathematical truth telling us that even within seemingly random, chaotic events, there's an underlying, stable, predictable order that emerges. If you just look at enough trials, short-term chaos becomes long-term certainty.
So maybe the takeaway for you listening is, next time you see a pattern emerging out of what looks like randomness, whether it's game results or market trends or even just daily coincidences, think about the law of large numbers. Consider why that pattern is appearing. What other parts of your world, seemingly unpredictable now, might just be waiting for enough data points to reveal their own hidden predictable heart.